Okay, so hello and welcome to today's lecture recap. And this is going to be our last lecture on thermodynamics before we transition to a new topic on Monday. So what we were talking about in the previous lectures this week was the concept of entropy. And we'd understood a microscopic definition of entropy, which was basically a count of the number of microscopic configurations corresponding to a particular set of macroscopic variables. So for a gas in a cylinder, we're looking at the temperature, pressure, and volume as our macroscopic variables. And we're asking, well, how many configurations of the molecules are there that correspond to that particular set of macroscopic variables? So that was a microscopic definition of entropy, the logarithm of that number. But then when we wanted to understand in practice, how do we calculate entropy or entropy changes for processes? What we found was that there's a much more useful formula that relates the change in entropy in a process to the amount of heat that flows into your system and to the temperature. And so that was this equation that ds equals dq over t. Okay, and so generally if heat flows into a part of a system, then its entropy increases. If heat flows out of a part of a system, then the entropy decreases. Okay. And our second law of thermodynamics basically says that if you look at the entire system, or the system and in the environment, so if you look at every place where heat is either going into or coming out of, the second law of thermodynamics says that the total entropy never decreases. So in this situation, if we have a flow of entropy of heat from the cold side to the hot side, using our previous formula, what we calculated last class was that would correspond to a decrease in entropy. Whereas if we have heat flowing from the hotter side to the colder side, that corresponds to an increase in entropy. And so according to the second law of thermodynamics, that flow from hot to cold is allowed, and the flow from cold to hot is not allowed. And we understood that microscopically as just the statement that there are vastly more configurations like the one on the left as compared to the one on the right. The entropy is just a measure of the number of such possible configurations. And so the statement of the second law of thermodynamics basically just says that because the transfer of energy between molecules is essentially some random process, that we're just going to be much more likely, almost infinitely more likely, to end up in a configuration like this compared with a configuration like this, because there are, we wrote it down last time, 10 to some enormous number, that number, 10 to the power of this enormous number, that many times more configurations similar to this one as compared to this one. And so we're basically just always going to end up moving towards something like this, where the temperatures are more balanced. Okay. So the other thing we understood last class about entropy is that it is a state variable. As I mentioned, it's just a count of the number of these microscopic configurations corresponding to a set of macroscopic variables. And so like these other macroscopic variables, P, V, T, and U, the entropy is something that we could just calculate based on the current configuration. So given P, given V, given T, and U, we could in principle figure out what the entropy is. And so that means when I have various processes from some initial configuration to some final configuration, and I want to know what is the change in entropy for these various processes, it will be the same for all of them. It'll just be the entropy at B minus the entropy at A. And for a full cycle, we also find that the entropy is going to be zero. The entropy change is going to be zero because we're coming back to the same configuration and therefore to the same entropy situation. One important point is that in such a situation, even though you come back to the same situation with your, say, your gas in a cylinder, and the entropy comes back to the original entropy, it may still be that the entropy of the environment increases. So that will typically be true. For example, whenever you transfer heat, if there's some transfer of heat from your system at one temperature to the environment, and if that's a different temperature, well, that's going to correspond to an increase in entropy, as we calculated the last time. Okay, so going back to this second law of thermodynamics, it's important to understand that it's the total entropy of the entire system, which includes the environment, that can't decrease. But sometimes we do find that the entropy of a part of the system decreases. As long as the entropy of the other part increases by more or the same, then we're okay. There's a special name for the kinds of processes where the entropy actually stays the same for the entire system plus environment. We call these reversible processes. And that's to contrast with a situation where the entropy increases. And that's clearly irreversible, because if you have an increase in entropy of your entire system, then the second law of thermodynamics says you could never go back to the original situation, because then that would require a decrease in entropy. Okay. So processes where the entropy increases, such as transferring heat from a hotter object to a colder object, those things are always irreversible. Okay, so during the rest of the class, we're going to explore a different way of making use of the idea of entropy. And it's going to actually lead us to some very efficient ways for calculating things like efficiency of an engine cycle, and actually analyzing these engine cycles. And later we'll, by the end of the class, be able to predict which engine cycle running between some maximum temperature and some minimum temperature gives you the greatest possible efficiency. Okay, so this idea of entropy is going to be very useful for us in practice. And the way that we'll use it is actually to think about representing processes on what's called a TS diagram. So this is an alternative to the pressure volume diagrams that we've been mostly working with so far in the course. But it's the same kind of idea. We have some process, but now what we're going to do is keep track of the temperature of the gas during the process, and keep track of the entropy of the gas during the process, and plot the process then on this diagram where entropy is on the x-axis and temperature is on the y-axis. So your first question is just to sort of indicate why this is going to be useful. Your job is to calculate how much heat was added during the process that I've depicted here on the temperature entropy diagram. Okay, so take a moment to think about that, and then we will discuss it. Okay, so let's have a look at this process. And so it's clearly a fixed temperature process. So in TS diagrams, isothermal processes are just straight horizontal lines. And we see that we're going from an entropy of 20 joules per Kelvin to an entropy of 80 joules per Kelvin. And we want to calculate the heat. So what we're going to do is start with this basic result that the heat and the change in entropy are related to each other. So if we rearrange this a little bit, because we're interested in calculating heat, then we have the statement that the change in the amount of heat for any part of any process is equal to the temperature times the change in the entropy. And so in this case, it's a constant temperature process. And so then what we could say is that even for the entire process, so if we add up the heat that's added during each step, then we could say that, the Q for the entire process is then equal to T times delta S. And what we realize is that the delta S is just this distance on the x-axis, and the T is the distance here on the y-axis. And so the T times delta S is actually geometrically the area of this rectangle. So working that out, we find that Q for the process is 200 Kelvin times 60 joules per Kelvin, and that works out to 12,000 joules. Okay, so the answer for that one is D, 12,000 joules. And more important than the answer was our realization that when we're talking about TS diagrams, we can actually geometrically calculate the heat in the same way that we geometrically calculated the work on a PV diagram. Okay, so actually let me, bring the camera back here. Let me just write down this mathematical analogy. So what we just learned is that by rearranging our formula for changes in entropy, we can write that dq is TdS. And this is reminiscent of the formula that dW equals P dV. And so essentially, everything that we said about calculating work using a PV diagram also applies to calculating heat for a TS diagram. So we don't really have to go through all of the arguments again. We can immediately say that the heat is going to be the area under the curve on a TS diagram. So in our previous example, we had constant temperature, and that area was just the area of a rectangle. In general, the temperature could be changing during your process, and then what we'd need to do to calculate heat would be to break the process up into many different parts, where for each part, the temperature doesn't change very much. And then we would use this formula to calculate the heat for each of those parts. And in each case, we would get a narrow rectangle, the area of a narrow rectangle with height T and width delta S. And when we add up all of the heats for each of the parts, that would give us the area of the sum of all those narrow rectangles, and that would be the area under the curve. Okay, so it's just like calculating work on a PV for a process plotted on a PV diagram. And similarly to that case, we can identify the sign of heat by looking at whether the entropy increases or the entropy decreases. So a process going to the right would have an increasing entropy, and going to the left, a decreasing entropy. And again, that decrease in entropy is not a violation of the second law, as long as the entropy of the environment increases by at least that much during the process. So here's another question for you. Making use of this new knowledge of how to calculate heat geometrically, you can try to think about what is the net heat that enters the gas during the cycle shown. Okay, so in order to do this one, hopefully you've had a chance to think about it. In order to do this one, we're basically just going to use our understanding that the entropy is equal to the entropy for any, the heat for any process is the area under the curve. And so in this case, we have this process here at a constant entropy, which would have no heat associated with it. So this is actually an adiabatic process. That's what they look like on TS diagrams. For this process going down here, we have a positive heat, which is going to be the area here under that sloped diagonal line. For this process here, that's a negative heat. And so we're going to have minus the area of this rectangle. And so the net heat for this process will just be the area inside the curve. So that was basically, we could have just deduced that immediately because that was how we calculated work for cyclical processes on a PV diagram. Okay, so the area here is equal to half the area of the base of the triangle times the height. And so that ends up being 1/2 times 80 joules per Kelvin times 600 Kelvin, and that gives us 24 kilojoules. Next question. Looks almost the same, but see, I've changed heat to work. So now the question is, what is the net work that is done by the gas during the cycle shown? So take a minute to think about that, pause the video, and then we're going to talk about it. So this one initially seems a little bit tricky because usually calculating work, we need to know about pressure and volume. And here we're given temperature and entropy. So the reason why it turns out to be relatively simple to answer this question is because we're asking about the net work for an entire cycle. And so in order to calculate that, what we can do is make use of the first law of thermodynamics to relate the net work through the cycle to the net heat for the cycle. And so because we're talking about a complete cycle, then we know that delta U is going to be equal to 0 because U is a state variable and we're coming back to the original state. And so that means that W net is equal to Q net for the cycle. Okay, so this is, I'm having real difficulty spelling cycle. Cycle. It's because I'm looking at this sideways. So in this case, we actually don't need to do any further calculation because in the previous question, we just calculated that the net heat was 24 kilojoules. And so again, what we can say is that the answer is 24 kilojoules. So that is D. And putting together the result of this question with the previous question, it's going to give us a very, very useful result that we can geometrically calculate the efficiency of a cycle that's plotted on a TS diagram. Okay, so what we just learned is that the net work or the net heat for any cycle is going to be the area inside the curve. It's positive if the curve is traversed in the clockwise direction, or if the cycle is traversed in the clockwise direction. If you have a counterclockwise section, we're going to get a negative result. Okay, and now we can make use of this idea in order to very efficiently calculate the efficiency of an engine cycle. So have a go at this one. Think about, just based on this information that we've been given, what is the way that we can calculate the efficiency for this particular cycle? Okay, so let me draw that out here. So I'll make use of this previous diagram here. And so basically, what we're going to use is just the definition of the efficiency, which says that E is equal to the net work for the cycle divided by the Q that goes in, just the positive contributions to heat. And so in this case, it's going to be easy for us to analyze if we replace W net with Q net. So the net heat for the cycle divided by the positive contributions to heat. And then what we see is that, as before, the net heat for the cycle is the area of the triangle, just the area inside the curve. And so that was 24 kilojoules. And now the area, the heat that goes in, we can say, well, which parts of this cycle would heat be going in? And those are the parts with increasing entropy. So that's only this diagonal line. And the heat for that part of the cycle is the area under the diagonal line all the way down to the axis. And so plugging in the numbers, what we have is that that area is the area of our triangle, 24 kilojoules, plus the area of the rectangle, which is 80 times 300, or also 24 kilojoules. And so the final answer is simply 0.5. So the efficiency is 0.5 because the area of the triangle is half of the total area under our top curve there. Okay, so that was very easy, and we can generalize that to the following observation that applies to absolutely any cycle that we might draw, even this very complicated cycle that isn't really even a combination of the simple processes that we usually talk about. So we've understood that the net work is always just the area enclosed in the cycle on the TS diagram. And we've understood that the heat that would be going in, that would be the area under all of the right moving parts of the curve. And so that corresponds to this orange area in the diagram here. And so we learned that the efficiency is just the ratio between the green area and the orange area. And so if we want to evaluate the relative efficiency of two cycles, we can do that very easily if the cycles are given on a TS diagram. Okay, so just compare that to how much work you had to do in homework 6 to calculate the efficiencies of those various cycles on the PV diagram. It's just much, much simpler once we know about this idea of entropy and we're able to represent the cycle in terms of the entropy and the temperature during the process. Okay. So using this new understanding, we can get to an amazingly powerful result very simply. And so you may have been wondering in the past, which kind of a cycle would actually provide the most efficient engine in principle? And so in order to answer this, we're going to place some constraints on the design of the engine. And we're going to say that we want an engine cycle that operates between some minimum temperature and some maximum temperature. Okay, so maybe the minimum temperature would just be the temperature of your surroundings, of the air or the surroundings in which your engine is operating. Or maybe you have some particular cold reservoir, some ice that's out there naturally. And so that would be the minimum temperature. And then maybe there's some maximum temperature that we don't want our engine to go above in order to, make sure things don't melt and so forth. And so we're going to place these constraints on the engine cycle. And we want to know what is the maximum possible efficiency that we can have operating between these two constraints. So this is an interesting question. And so see if you can answer that question based on the geometrical understanding of how to calculate efficiency. Okay, so let's talk about it. So we have our minimum temperature, our maximum temperature, and we could just start out by drawing some arbitrary process that's running between these two temperatures. And now we can ask, so we have the efficiency, and it's like the area of the inside divided by the area below the topmost curve. And so, all right, A in divided by A below, and by below I mean below this top curve here. Okay, so in order to answer our question, we could think about what do we have to do? What could we do to this cycle to actually increase that efficiency? And so the first thing we can ask is there any way to increase the area inside the curve, but not increase the area below this top curve here? And there we could see that we could actually modify our cycle. If we modified our cycle to be this, to have a rectangular bottom like this, then what we would be doing is adding this area here So now this would be part of the area inside, but it wouldn't change the area under this top curve. And so that would clearly be more efficient. Now we can ask, is there anything else we could do in order to increase this efficiency? And it's not quite as obvious, but it's relatively easy to argue that if we also extend our cycle to be rectangular at the top, so to be like this, then this also increases the efficiency. And so the reason is that that adds on this shaded area here. Maybe I should draw it in a different color. Let's actually make that top area shaded blue. There we go. So the blue shaded area, it increases the area inside the cycle, but it also increases the area under our top curve. And so that increases both the numerator and the denominator. But what you notice is that it's a larger percentage increase for the numerator here than it is for the denominator. So we're adding on the same area to the numerator and the denominator, but the numerator is already smaller than the denominator. And so we're going to definitely have a greater percentage increase for the top than for the bottom. And so basically that means we're multiplying the top by some number, like 1.2 if it's a 20% increase. We're multiplying the bottom by a smaller number, like 1.1, maybe it's a 10% increase. And so overall, we'll be multiplying the efficiency by a number which is greater than 1. Okay. And so we've now understood that by adding these corners on to the process at the bottom, and then also adding on the corners to the process at the top, all of those things increase the efficiency. And at this point, there's nothing more to add on. We're already right up against the top boundary, and we can't further deform the curve without going above our maximum operating temperature. And we can't further deform our cycle without going below our maximum or minimum operating temperature. And so this is the end result. This is the maximum possible efficiency that we can get. So, okay, so that's kind of amazing. We've understood just geometrically what is the maximum possible efficiency for an engine cycle running between a hot temperature TH and a colder temperature TC. And because this is such a special cycle, it has this maximum possible efficiency. We give it a name, and it's called the Carnot cycle. So just quickly, we can take a moment to calculate what that efficiency would be. Think about it and choose one of these answers. And then I'll say a little bit more about this Carnot cycle. Okay, so it's a fairly straightforward calculation. We want to know the ratio between the green area and the orange area. And these are just the areas of rectangles. And so because the width of these two rectangles is the same, then the efficiency is going to be the ratio between the height of this rectangle and the height of the orange rectangle. And so that's TH minus TC divided by TH, or equivalently 1 minus TC over TH. Okay. And so you see with a minimum operating temperature TC and a maximum operating temperature TH, then the maximum possible efficiency that you're ever going to get is 1 minus that ratio. So if you wanted an interesting point there is, if you want an efficiency that actually approaches 1, you really need to take the lowest operating temperature, like the cold reservoir temperature or the minimum temperature of your cycle, to be very cold, as close as you can to 0, or take the highest temperature to be as hot as you can relative to that cold temperature. But then you run into various constraints on, say, the materials in your engine. Okay. So here is a summary of that Carnot cycle. It was very simple on the TS diagram. We have a constant temperature process here, a constant entropy or adiabatic process here, constant temperature here, and adiabatic here. If we want to go and plot that on our PV diagrams, it looks a lot more complicated because remember, isothermal and adiabatic processes are curved, but curved in different ways. Okay, so the adiabatic processes have a quicker decrease as we increase the volume, and the isothermal processes have a slower decrease. And so putting it all together, we get a diagram like that. Okay. One point is that even though this is an engine cycle with the maximum theoretical efficiency, it's not usually that practical to actually base an engine on this thermodynamic cycle. And the reason is that for isothermal processes, these usually have to happen very slowly. So if you want the temperature of your gas and the temperature of the surroundings to be the same during a compression or an expansion, then you need to perform that compression or expansion extremely slowly. And so if you want an engine which is maybe operating at many cycles per second, then this is just not really a practical design. Okay, so the Carnot cycle, it's an interesting theoretical tool to understand what's the best we could possibly hope for, but then in practice, we usually sacrifice some efficiency in order to have an engine that works in a practical way for our application. Okay. So that's all for today. And that's all we have for the thermodynamics portion of this course. Next week, we're going to start in talking about oscillations and waves, which are basically, in terms of our general setup for the course, the thermodynamics is like understanding random motions of molecules in a solid or a gas and all the various aspects of these random motions. Whereas when we talk about oscillations and waves, these are going to be collective motions of molecules in solids and liquids and gases, where many of the molecules in a region are actually moving together. Okay, so that'll start next week, and have a great weekend.